So hello everyone, my name is Nitesh and I welcome you to Uncovering Azure's Silent Threats, a journey into cloud vulnerabilities. So a little about myself, I'm from Sikkim, India, and I'm really honored to be here at BSides Ahmedabad. I work at Trend Micro with a focus on cloud and container threat research, so mostly studying attackers by building honeypots. So I've been in the threat research space for around 2.5 years now, and I'm also a member of Null, an open security community. So the fun fact, like I wrote my first song in 2018 and my first exploit in 2009 when I wanted to win at a game called Project IJ, like the host said. And this is a picture from my last trek where I went on with my friends, like a 4-kilometer trek, very small, but I have an ACL tear, so it was a very big thing for me. But why are you here today? Today I'll be talking to you about a journey of exploring the iceberg of a cloud-based machine learning as a service offering. To make things simpler, we'll go through a few episodes, an introduction of what we are going to talk about, the issues that we uncovered while exploring the service, and we'll drop to the conclusions and takeaways. So this is an expanded version of my previous talk from Black Hat USA this year. And this is a talk about the security issues that we found in the hottest machine learning as a service offering currently known as Azure Machine Learning Service from Microsoft. So let's begin the journey. So there has been some buzz around cloud service providers fixing vulnerabilities reported in Jupyter Notebook-based services across Azure, AWS, GCP. So is there something off or something fishy with notebooks in general? So I pack my bags and I head to the Azure portal searching for services that are based on Jupyter. And I come across this one interesting result which talks about running Jupyter notebooks in workspaces. And folks, this is where it all started. In 2019, there was a prediction in a Gartner report which talks about a 5-time increase in the usage of cloud-based AI services by 2023. And in 2023, it kind of makes sense as companies are seeking to use AI in their product services. They want to create ChatGPT-like chatbots. They want to train LLMs on custom data sets. And even when ChatGPT was released, I was a little curious to know how does the underlying platform look like and how can one leverage the same platform. And this video clip from May this year kind of makes sense now. So the AI offering in Azure looks something like this. On the top, we have certain problem-solving services. And on the bottom, like the cognitive services, we have the machine learning models as a service. And everything that you see in the highlighted box is actually built on top of Azure Machine Learning Service. So AML is a mammoth of a service, and we'll go through some basic terms first to understand the issues that were found. So it's a machine learning as a service offering. It uses a mix of user-managed and Microsoft-managed services to function. In AML, you basically create a workspace, which is like a centralized place to manage all your machine learning activities. You can access the workspace using a browser, VS Code IDE, the Azure ML CLI as well. But what do you do on a workspace? You basically work. You create Jupyter notebooks, you can run your experiments, you can create and import data sets, you can create training inference environments, you can also deploy these machine learning models as endpoints, and you can do all of this just from the browser itself. So that's pretty cool. The workspace is dependent on certain Azure services on the user's end. So when you create a workspace, there are resources for these services like the storage account, key vault, application insights that are created on the user's subscription, except for the container registry. So it's not mandatory to have an ACR, like an Azure Container Registry, configured to create a workspace. So in AML, users or data scientists would basically perform MLOps, and these are the various compute targets that are provided by AML for a user to run the Jupyter notebooks, training scripts, or host your machine learning models as endpoints. So you have compute clusters, which are like clusters of virtual machines, so you can scale them as per your requirement. You can have your on-premise Kubernetes clusters or AKS as well. You can attach them as well. You have attached compute, so you can attach any like virtual machines that you have, and you can run your scripts on it. And specifically for this talk, we focus on compute instances. So compute instances are basically managed Ubuntu virtual machines that reside in a Microsoft subscription. By managed, we mean that these resources are maintained by Microsoft, like patching of the host OS, if there are any issues found, patching of those issues as well. And the OS image contains a lot of tools that are used by developers, like Jupyter, VS Code, Docker, Python, and all these deep learning libraries and stuff. So basically, this is where you run your code, and you perform your model training, etc. And each workspace has a storage account which contains your machine learning related entities. So to access the data in a storage account, you use something that is called a data store, which are basically a reference to the storage account for the Azure Machine Learning workspace. So using data stores, you can actually avoid storing your access keys in scripts and like SAS credentials in your scripts. And you can simply use the data store to refer to the storage account. Okay, so it's like just a reference. And there are file shares and blob containers that are used to store notebooks, datasets, logs, models, and like this is basically where all your stuff is stored. Okay. So we can browse the storage account using Azure Storage Explorer, and we can view the file shares and the blob containers that are referenced by the data stores as well. So these are certain default data stores. So on the left that you see workspace artifact store, that is the name of the data store, and the type of storage it references is Azure Blob Storage. And on the right, you have the screenshot from the Azure Storage Explorer. Just take a note of the blob container names like Azure ML and Azure ML-blob store-some UUID. So this is how it looks. The data store name is workspace working directory. The type is file share, and the type of file share it references is defined in the box below, and the account name as well. So that's pretty fine. And the data stores in Azure Machine Learning Service, they support a credential-based authentication for file share. This basically means that if you want to work with file shares using data stores, you will be using a combination of a username and a password, where the username is the storage account's name, and the password is the storage account's primary access key. Additionally, multiple users can create compute instances in a workspace. And by design, there cannot be two owners for a compute instance. Also by design, any user can access the other user's files in the same workspace. It's a shared environment. So the created compute instances share the workspace's storage account's file share, as the file share is mounted on all the compute instances in a workspace. So with this background and a very simple basic introduction of Azure Machine Learning Service, we begin with the first episode where a data scientist is looking for the keys. So while examining the different folders and the files on the compute instance, we come across a directory structure which looks something like this. So applications, FS mounts, shared, startup, volatile, work items. So this directory structure is of Azure Batch, which is a different service. So we take a quick look into what Azure Batch is. So using Batch, you can basically run large-scale workloads in Azure with auto-scaling and monitoring as well. So for example, if you want to process images at scale, like you want to have your 100 nodes, then you can just do that using Azure Batch. And these are some basic terms to understand as we proceed. Because it's a journey, so it's a journey of cloud vulnerabilities. We need to take certain pauses. We need to get a little uncomfortable, and then we learn again. So compute nodes are Linux or Windows virtual machines. The group of nodes is called a pool, and so basically you can group nodes together. The jobs are collections of tasks that are run on a pool where you have your compute nodes, and you can think of tasks as individual run of a job. So for example, if you are testing the output or the performance of a script, then you run it 10 times, you compare the metrics, and then you figure out, okay, the script is doing fine or not, right? So that's a job, and each individual run of that job is called like a task. And you can monitor and download the output logs for tasks. So in batch, you have a concept of a start task. So basically, the start task runs when a node starts up. The files, the configurations, the output of the task, they all are stored in this path in blue under tasks startup. And the output of these tasks are actually stored in like error logs like standard out and standard error. So as we saw previously, the file share is mounted on a compute instance. So we had a question, how is the Azure file share being mounted on the compute instance? Since it uses credential-based access only, it would be interesting to examine if there are any credentials being logged or stored in clear text on the compute instance. So we found that the output of the start task is logged in standard error and standard out files in this path. And we saw that the storage account credentials were being logged as is in the standard error logs. And since the command runs as sudo, it also gets logged in the authorization logs. So we reported these two instances to Microsoft and we waited. A few days later, we came across an instance where the password field of the entire command line was masked. Note that the commands executed in the start task on the compute instances are also authored by Microsoft. So this was the fix. That left us wondering, if there are more such instances of credentials being logged, let's just report them to Microsoft. So we started looking for more. So Azure Machine Learning uses certain agents to manage compute instances. So these agents are basically some services that are used to diagnose, monitor, and make sure that the compute instance is healthy, or just troubleshoot stuff. So these agents are located in the working directory under the start task. And these agents need certain configurations to perform actions. Like, they don't act on their own, they need certain configurations. And these are provided in the form of environment variables. So these environment variables are again stored in files, which is under the working directory DSI. Okay, so we found that the configuration for two of such agents named DSI mount agent and DSI idle stop agent contained the storage account's primary access key. So the environment variable was named passwd, and that contained the storage account key, but we were left wondering, like, it could have been something else, like password or storage account or something else as well. So it turns out that the password argument can be supplied as an environment variable named passwd. And this issue was found while trying to understand how were the previous issues fixed. Nevertheless, all the instances of storage account credentials being stored or logged in clear text were fixed after our reporting, and that brings us to chapter 2. Since credentials being logged and stored in files was acted upon and fixed, we had a thought. Are there credentials incoming on the compute instance? And with that, we begin chapter 2. Wait, is that my token? So a user can access the compute instance from the browser using Jupyter Notebooks, Jupyter Lab, browser, terminal. So these requests are actually proxied to the compute instance by a load balancer / proxy in between. So basically, if you want to access Jupyter Lab on a compute instance named AML in the East Asia region, the URL would look something like this. We do not have access to the load balancer's logic here because it's maintained and owned by Microsoft. So this is how the Jupyter Lab UI looks when you access from the browser, and this is how the browser embedded terminal looks in the Azure ML Studio. Oh yes, the default user, Azure user, can assume root privileges without needing a password, and we'll use this bit later on. So these browser-based terminals can be accessed by your user with the proper role-based access control permissions. And the authentication flow for a client looks something like this. So the client logs into Azure AD or Entra ID, maybe not a good idea to call it right now. And they are presented with an ARM token, which is the Azure Resource Manager token. Now the client uses the ARM token to talk to the Azure Machine Learning Service, which in turn generates a new token, that is the AML token, which is scoped to the workspace to perform AML actions, and this token is used from then on. All incoming requests to the compute instance are received by an Nginx proxy that is listening on a fixed port, that is 44224. It has SSL enabled, and there are certain certificates that are used from the above highlighted paths. So client-side certificates are validated by this proxy configuration, and there are certain checks on the subjects and the issuers as well. So the proxy checks whether a header named XMS target port, separated by hyphens, contains a numeric value. Later, the value of the header is used to forward the request to the appropriate service. So for all incoming requests with the URLs containing Jupyter-related APIs, the request is upgraded to the WebSocket, and the requests are forwarded on the basis of XMS target port, header in the proxy pass directive. So basically, an incoming request on the compute instance shall have this header populated, XMS target port. This request will be received by Nginx service listening on port 44224. And based on the value of this header, it is 8888, which is also the default port for Jupyter. The request is forwarded to localhost, 127.0.0.1, and then the interesting bit here is the Nginx, in a default configuration, Nginx also logs your access and any errors that are generated. Cool. We found an issue using our good old friend called TCP dump to view the network capture, that what happens when you terminate a browser-based terminal, basically. So when you click on close and you hit on terminate, there are certain requests that are sent, like a GET request is sent followed by a delete request. And if you notice, the GET request has a URL parameter named token, which contains a JWT. And who did the token belong to? The token belonged to the user, so it was the ARM token. And it turns out that we had the JWT of the compute owner that was being logged in the Nginx access logs because it was there in the URL parameter. So while trying to figure out why was this even happening, in the documentation of Jupyter Server, we see that there are 3 ways to authenticate to a Jupyter Server. So one of the ways is to use an authorization header. The other is to pass it as a URL parameter. And the third is to specify the password in the login form. And since Nginx logs the access attempts, the access log actually contained the JWT token. We reported this issue to Microsoft, and they promptly fixed it again. Now, after all, these are just credentials being logged or stored in files on compute instances. What could go wrong and what is so risky about it? So developers have been observed sharing error or debug logs from their systems on public platforms like GitHub. If they are not aware of the fact that these artifacts at times may contain credentials, that too in clear text, that's a silent risk that they're being exposed to. In this example, we see certain folks discussing on GitHub, they are requesting for batch error logs, which in our case contained the storage account access key in clear text. However, this instance is from 2018. It's a pretty old instance, but let me show you something new. So does anybody recognize this URL? I cannot see the audience, but I'll assume no. Okay. So we have a storage account name, and this is like a SAS URL being used to access a file named FGVC aircraft 2013B tar GZ something. Okay. So what is happening? We have a storage account name that is robustness, wwws, something. Cool. The types of services that can be accessed on this storage account, that is the blob, file, queue, and table. The APIs that are accessible for the storage account, that are the service, container, and object level APIs. And the permissions are root on the storage account just from this URL itself. And the expiry of this URL, or the SAS token for this URL, is 2051. This URL is actually related to a recent finding from researchers from Wiz, where they found an overly permissive shared access signature token, like a SAS token, for a storage account on public GitHub repositories of Microsoft. It basically allowed them to access 38 terabytes of data, but this was like a over permissive token, so you could basically take a look into the entire storage account, which also contained backups of like 2 former employees, and it was like all over the news some time ago. And by default, the storage account in Azure Machine Learning Service is publicly accessible. And this is just a speculation. If you notice the blob container names that are Azure ML-blob store and Azure ML, that's the similar container names that we saw for the storage account that we were exploring in the first, like in the introduction. So mistakes happen, and it's pretty human, but we need to keep learning and trying not to repeat them. We have a couple of more findings that will be hopefully presenting sometime related to SAS tokens itself. So dependency confusion attacks with attacker control code has been known to be exfiltrating credentials from files after gathering them. So this is the case of a popular library called PyTorch. The nightly build of this PyTorch library was compromised December last year, and the binary would basically exfiltrate credentials from scripts, environment variables. And this was targeting machine learning environments primarily because PyTorch is primarily like used in that context. So if an attacker is able to compromise a file share, they can very trivially compromise the entire storage account and the entire workspace too. Let me show you how. So consider a scenario which might be likely to happen. There's a workspace with 3 data scientists, each having 1 compute instance. By design, we know that each workspace user's files are stored in the same Azure file share. If an attacker can get hold of a user, which is, again, a very high degree of compromise, but that's how you threat model things, or a compute instance which has these credentials being stored or logged in clear text, or the file share where you have your Jupyter notebooks, scripts that are run on compute instances and compute clusters and everywhere, the entire workspace should be considered to be compromised. Now you picture this with a scenario where users could view each other's JWT token being logged in the Nginx access logs. Suddenly the issue becomes massive because of the design of the environment. According to the docs, data stores provide a way to secure your connection information, such as storage account, access keys, and SAS creds. Using them, you don't need to store these credentials in your scripts, and that's very cool of a feature. However, if the storage account key itself is being logged in error logs, authorization logs, environment variable files on the compute instance, That kind of creates a difference. And the default user, Azure user, can easily assume the sudo privileges, so user privilege is not really a boundary here. Now, the same issue of credential logging may have been in your environment if you were using Azure Machine Learning Service, but on Valentine's Day this year, Microsoft released a CVE for this finding. Now, the JWT is not observed to reach the compute instance, and the storage account access key is not logged or stored in any of the files on the compute instance. Some takeaways. Be it logging or storage of credentials, credentials in clear text is bad, that too in user shared environments like Azure Machine Learning. From the design of such environments, we need to be aware of the risks as well. While using open source tools, we also need to be aware of the configurations that they have. Like if the JWT of the user was reaching the compute instance, that's still fine, but logging the token in a file, probably not. Sensitive information should not be shared as URL parameters, as you never know there are inline proxies or where the request is getting logged. So this is also echoed by researchers very long back. And additionally, developers need to be aware of possible security implications that may show up while sharing information on public platforms. The issue of credential leakage can turn out to be very critical, especially when users may not be aware of them, as we saw in the case of the accidental leak of 38 terabytes of Microsoft AI data. With that being said, now we embark on the third and almost final chapter of spying the scientist. So in Azure ML, you can create compute instances in virtual networks. You can specify the virtual network and the subnet during the creation of the compute instance. This can be observed in scenarios where the training environment needs access from or to other Azure services via private networks and not over the internet. And using VNets is also recommended by Microsoft in their documentation. A simple environment would look like this. The virtual machine lies in a virtual network, which is on the user's subscription. Remember that the compute instance is a managed compute, and it lies in the Microsoft's subscription. And on the same VNet, we have a compute instance. Let's say the virtual machine on the user's end gets compromised. What could an attacker do from the virtual machine on the compute instance? Were there any ports open? Let's find out. So we fired up our next favorite tool, Nmap, and we checked for open ports, and we come across a port called 46802. Since we have the compute instances access, we are able to figure out what is the process that is listening on this port. It's called DSI mount agent. And the process runs with root, like the high privileges. And it is written in Go. It is closed source, so it's not like WA Linux agent or OMI that has been talked about before. And we don't find any references in the public domain. But we have some debug information to understand what the binary is doing, as the binary is not stripped. Like we have the debug symbols. Now we crack open the binary using IDA to understand what is going on. And we come across a function called DSI start API service. So this service exposes certain HTTP endpoints on that port. And just a reminder, there is no authentication required for network adjacent resources to access these URLs. Perfect. So we start taking a look into the different URLs, and we try to figure out what they actually do. So the first one executes sync command on a file. The second one executes the mount operation. The third one helps us view the compute instance's image version. Nothing specific, nothing interesting. But the fourth one lets us view the service statuses on the compute instance. So examining the services endpoint, one could list the status of each service installed on the compute instance. We also see that we could see the logs of any service that is installed on the compute instance. So a network adjacent attacker could basically list down the services installed, the status of the service, the logs for any of the service, and this information could basically help them in reconnaissance for performing further lateral movement once they are post in the environment after initial access. And okay, that's cool. But as an example of what all could be exposed, here's a short little demo of what could a network adjacent attacker really see. So while exploring the installed services on the compute instance, we see that Jupyter is installed as a service on the compute instances. Now this is across any compute instances that you will be using Azure Machine Learning Service. And for each service installed, remember we can view the logs being network adjacent, and there is no authentication required for this. Turns out there were certain commands that were being logged in the Jupyter service, and folks, this is where I went What did just happen? We saw some commands being logged in the Jupyter service. So instead of Jupyter, there could have been some other service as well. Simply put, let's say a network adjacent attacker gets on, like an attacker gets on a virtual machine which is part of a virtual network. On the same virtual network, you have a compute instance. The compute instance has this agent called DSI mount agent that is fetching the systemd logs, and it exposes an API on a hard-coded port that is 46802 across all the interfaces. And if there is a user or a data scientist who is using any form of Jupyter, be it Jupyter Lab, Jupyter Terminal, the browser-based terminal, to run commands as sudo, an attacker from the virtual machine could basically view the commands executed by the data scientist. And yeah, now if you remember the mount command that was being run in the first episode, that was being run as sudo. So that's just one example to show you how this could be exploitable in scenarios. So this is a short little demo of hacking the data scientist. We named this vulnerability MLC. So on the top, we have a compute instance where the data scientist runs like sudo cat etc shadow, and on the bottom, we are just fetching the logs for the Jupyter service from an attacker VM, and as you can see, we can view the logs. Now I will run the command to mount a file share on the compute instance, and the same command will also get logged on the network adjacent attacker VM. So this issue was fixed as a network adjacent attacker could possibly see the actions performed by a data scientist on their compute instance without needing any authentication. So this was a funny information disclosure bug. Now, the service does not even expose the port on all interfaces. All the traffic reaching the compute instance is coming via the Nginx proxy, which listens on port 44224, and you need client-side certificates to get through the proxy. Okay, some takeaways. So secret agents may lead to secret bugs and hence an expanded invisible attack surface, also a silent threat. So cloud service providers also should look into the attack surface introduced when using such agents in managed services like AML, where these agents may leak sensitive information. So there is a need for focused threat modeling on agent features, because certain features may be very helpful for the cloud service provider, but they may add vulnerabilities in secure configurations as well. Plus, practicing zero trust is hard, but it's very crucial for cloud security, because the essence of zero trust is like, do not assume that just because something is in your environment, it should have access to other resources in your environment. Additionally, simulating attacks in secure configurations, so like using VNets is one of the secure recommendations from Microsoft, can at times help you uncover vulnerabilities in the service itself. Okay, so the fourth chapter is Can You Really See Me? And I had to put John Cena because why not? Let's say we have a virtual machine and a compute instance, and we want these Azure resources to access certain other services. One of the ways is to hard-code credentials, but that's not a recommended way. So Microsoft recommends using something that's called a managed identity. So the logic behind managed identities is that if you want your application to access a resource, the application will request for a token to work with the resource from a managed identity service, and the returned token will then be used to interact with the resource that you want to interact with. The managed identity service can only be reached from within the resource. It's similar to the instance metadata. And you as a developer don't need to hard code credentials in your applications or scripts, and this is pretty cool. So you can assign privileges and roles to the managed identity that you create, and based on that you can get a token, and you can use the token to talk to the service that you want to talk to. So managed identities are of two types, a user-assigned managed identity and a system-assigned managed identity. So the user-assigned managed identity can be assigned to multiple resources in Azure. So basically, they can span across multiple resources. And a system-assigned managed identity can only, they are tied to the resource itself. So they cannot expand, span across resources. And only the Azure resource can request for tokens for both the identities. Cool. On a compute instance, one can sign in using the managed identity using the Azure CLI. So using managed identities, you can assign certain privileges and all that stuff, but when one runs az login -- identity, I was curious to know how does the traffic look like? What happens in the background? So we ran TCP dump and checked for any outbound traffic, when we run AZ login identity. And we get this get request with some interesting headers containing a secret header. But the request is still being sent to a local IP and port, as we can see from the host header. From the port information, we pull out the process that is listening on 46808. And the process is named Identity Responder Daemon. The process belongs to a service that is called Azure Batch AI Identity Responder Daemon. And it uses a bunch of files with various environment variables. It logs output and error logs to syslog, and that's helpful. But responding identities? While understanding the binary, we found that the binary fetches the secret and the endpoint, the MSI endpoint and MSI secret, from this particular file at hcenvironment.sso. But even now, the request is still being sent to a local interface. I was curious to know, where is the final request being sent? Is there some public endpoint for this? So for analyzing the binary, just for fun, I had a moment of deciding whether to dump the process, check the logs for the service, or reverse the binary. But since this is our game, we set the rules here, and so let's just go all in. Here we have the syslog entries for Identity Responder Daemon, and as you can see, it reads some file that is in mount azmount.nbvm, and it fetches certain API endpoints like the get a new token from East Asia cert API and stuff. So basically, okay, it fetches environment variables from these two files, and it basically talks to a public endpoint. And the final request to fetch the Azure Machine Learning JWT looks something like this. So we have the compute instance name as instance ID in the post body parameter, the certificate thumbprint, and the resource for which we are fetching the token. Okay. And there are certain certificates and private keys that are used from this hard-coded path. Cool. So consider a scenario where the Identity Responder Daemon basically talks to the cert URL using a pair of certificate and private key, and it fetches the AML JWT token. Okay. Consider a scenario where the certificate and the key combination have been exfiltrated after compromise. So the thought is like, can an attacker use these certificates from non-Azure environments to fetch the JWT token? Turns out the attacker got like a 401 unauthorized. So, okay, so the thought is, the assumption rather is, the certificate and the private key are tied to the compute instance, and they cannot be used from outside the compute instance. And that's a good thing. But does the story end here? Not yet. So have you played this game called Return to Castle Wolfenstein? So this is my version of Return to Castle DSI Mount Agent. Please laugh. So now we take a look into our good old friend, DSI Mount Agent. The service fetches its environment variables from a file that is DSI Mount Agent env under DSI working directory. This agent runs as a service on every compute instance, and the environment variables look quite interesting. We have something cool going on here, like keys, certificates, some XDS endpoint. What is all this about? Checking the systemd logs, we figure out that the DSI mount agent basically checks whether the file share of the workspace's storage account is mounted on the compute instance, and it checks for this every 2 minutes, like every 120 seconds. Okay, but to work with file shares, we need the credentials, right? The storage account name and the storage account access key. Turns out the agent talks to an endpoint that is defined in the DSI mount agent env environment variable file, and it uses the certificate and private key from the same path that we saw earlier. And while examining the outbound network traffic from the compute instance, we were able to create this post request. We need to focus just on the post body, that is the request type, and like whatever that is there in the post body basically. So in this case, we have the request type set to get workspace. And from now onwards, the post request URI and the headers look all the same, so we'll be just focusing on that request body itself. By reversing the binary, we figure out that the function that is like sending this request type is get workspace info. Okay, the response contains the metadata about the workspace, and this can be considered like the who am I of the AML workspace. So you have the resource IDs for storage accounts, key vaults, application insights, container registry, and some metadata about the AML workspace itself. Cool. Later, when we were debugging the agent and we were trying to figure out what are the other request types that can be requested, we have one more candidate that is called get workspace secrets. So what secrets are we talking about? This looks very promising. In the response, we get the storage account name and the storage account's access key encrypted, encrypted in the form of JWT basically. It's called a JWE. So the JSON web encrypted format. So since we have the storage account name, it's highly likely that we have some way to decrypt this token, but let's find out. Upon understanding how the decryption of the token happens, this is how it looks. In a nutshell, two environment variables that are defined in the environment variable files, the encrypted symmetric key and a private key, they are used to fetch the, they are basically used to create the decrypted symmetric key. So this decrypted symmetric key can actually decrypt the response that we saw in the previous slide to get the storage account's access key. Okay. And for this, I thank my colleague David, so he was able to help me with the reversing for this aspect. Okay, so with a bunch of certificate and private key and the environment variables, if these three files are stolen, anybody could basically fetch the storage account's access key from non-Azure environments. Okay, so if these jewels are compromised, an attacker can fetch the credentials, right? Cool. But there is this concept in Azure Storage that you can rotate the credential. So does rotating the key help? We'll find out. Okay, so I go to the Azure Machine Learning workspace, and there is a storage account that is associated with this workspace. Now if I go down and if I see the access key, I will first copy the access key that is already there. So copy. So on the right, you see a terminal that is there on my laptop where I have the certificates and the environment variables already exfiltrated from a compute instance. And as you can see, I can fetch the decrypted storage account access key from non-Azure environments, like basically my laptop, using the certificate. Cool. Now if I rotate the access key and I synchronize my workspace to use this rotated access key, so I'll first copy just to show you that it's the same one. And I'll run the synchronization command. So basically, this will update the storage account key to be used for the Azure Machine Learning workspace. And now this synchronization has completed. And now I will rerun my POC. And we can see that we got the rotated storage account credential using the same bunch of certificates. So if your jewels are stolen, even rotating the access keys don't help. And this is quite persistent already, obviously, after post-compromise. And is there a way to track the usage of this certificate and the environment variable combination from non-Azure environments? We'll get to that in a bit. But let's find out what else can we do. Since we had get workspace info, get workspace secrets, can we find something new? So the function get workspace secrets actually calls another function that is called generate XDS API request schema. So this method in the same binary is basically used to generate the post requests body. So the idea was to look at all the cross references to the function that generates the post request body. That pretty much makes sense. And we have some candidates like get ACR token, get ACR details, get application insights, instrumentation key, and all that stuff. Cool. We found one of those functions in one of the binaries that is called get AAD token. To figure out how does the request body look like, we debug the agent to find the arguments being supplied, and we find resource, client ID, API version, and stuff. Cool. So the request finally looks like this. We have the request type set to get AD token, and a request body where we have a nested JSON, which is resource for which we are trying to fetch the token, which actually makes sense. You fetch a token for the resource that you want to access. And okay, cool. And in the response, you get the Azure AD token of the system assigned managed identity of the compute instance. Okay. So this was a little out of scope for the talk, but this is a recent development. So you could specify the client ID in the request body itself. In the request body itself. And you could yield the user assigned managed identity token from non-Azure environments. As you saw earlier, user assigned managed identity can span across different resources, and at times it may be overprivileged. So the compromise, So the compromise of the certificate and the key and the environment variables, can lead to fetching of the Azure AD token of the managed identity as well, and you can use the token later to move laterally or something. That's open to the privileges, based on the privileges assigned. But why does all of it matter? While skimming through the documentation, we come across this particular statement where, by design, only the Azure resource can use the managed identity to request tokens from Azure AD. But in our case, we are using the certificates and everything from non-Azure environments, impersonating the managed identity or the resource, and that was like a deviation from what was expected. Quick recap. So the agent, DSI mount agent, talks to this batch XDS endpoint, and it uses a pair of certificate and a private key. And you could basically fetch the who am I of the AML workspace, the storage account's primary access key, the Azure AD token of any assigned managed identity, and a lot more. So could an attacker if they had the certificate and the private key, which is, again, a very high degree of compromise, but we are just trying to understand like why this issue was even there, because for identity responder, I was getting a 401, but for these requests, I was getting a 200 OK. So this is a demo of fetching the tokens from system assigned and from non-Azure environments about system assigned and user assigned managed identities. So here we have the certificates and environment variables exfiltrated from 2 compute instances. So they have user assigned and system assigned managed identity. So in this case, I'll be fetching the workspace storage account credential. So I'm doing this from my GitHub Codespace instance. And as you can see, I'm able to fetch the storage account key as well. So yeah, now I can fetch the storage account, the AML workspace's metadata. So this is the who am I of the AML workspace. Now this is followed by fetching the, this is Sammy. Yeah, so this is Sammy, and this is like a very recent demo. So we are fetching the system assigned managed identity token from non-Azure environments using the certificate and private key. So we get the JWT in the response. So this was a deviation from the design and the expectation that we had. And similarly, we do the same for user assigned as well. Okay. So in this case, we just fetch the JWT token as is. And as you can see, we can fetch the token deviating from the documentation and the expectation and how managed identities are supposed to work. And this issue is still under analysis from Microsoft. But since the issues were reported via ZDI, so we have a strict disclosure policy of 120 days, I guess. So it was over 120 days. Cool. So how do the logs look? So you may be thinking, okay, if the certificates and the private key gets exfiltrated, I can still figure out from the logs, but let's see. So here is the legitimate activity where we fetch the JWT of the managed identity assigned to the compute instance. And here we have the malicious activity where the attacker has already gained access to your certificates, and we fetch the token from a non-Azure environment. Well, the logs were not very different. So this is the diff between the logs generated when the attacker does that and when we do from a compute instance. And the activity details don't have any sign-in, there's no IP address to figure out, okay, whether this request was done from non-Azure environment or from Azure environments. So the observation was that the logs are almost identical. The location info was missing. The certificate that we saw, it is valid for 2 full years. And to invalidate the stolen certificate, you need to delete the compute instance. And if there are any over-permissive identities, then it can open up avenues of lateral movement, privilege escalation, anything that you can think of. So some takeaways from this 4th episode. So you need to have your cloud service logging enabled and in place, because that is the most important thing, most important artifact that you can leverage to figure out, okay, what happened in your environment. So the logging for managed identity could be done better. You need to scope your identities following the principles of least privilege. I know we hear this a lot, but when you think of attackers who are quite persistent, who want to go stealthy, who want to find issues like this, you need to follow these principles and have your basics in place. So defense in depth with respect to cloud environments is a very important and a very good win. And definitely, you can threat model environments for possible scenarios of compromise where you can uncover such differences in the design itself. We found some bugs that rarely make the news, and they got fixed silently as well. We tried few angles as well. So where do we go now from here? You need to set up your environment using VNets, private links, and private endpoints. So the issue of storage account access key getting logged, the JWT getting logged, the agent exposing sensitive information, although it was in a VNet environment, having your defenses in place can help you reduce and eliminate these vulnerabilities at times. You need to focus and follow on secure deployment strategies and obviously go defense in depth. It sounds pretty generic, but it's very important. So in fact, Microsoft made it very easy to go secure by default by offering these network isolation options while creating an YAML workspace in the Azure portal itself. And you need to monitor your cloud environments for changes, any storage account keys getting rotated, public access or anonymous access is enabled. You need to perform regular audits as well, set up logging using cloud-native solutions. You can leverage frameworks like Azure Threat Research Matrix, Storage Matrix as well. Trust but verify, we all love this, but you need to verify the integrity of Jupyter Notebook's scripts, because when it comes to the threat landscape for machine learning systems looks a little different from what we have observed before. You need to examine and manage services to uncover silent threats. So this is also for researchers, bug bounty hunters. Just take a look at it, go on with your web application skills, and maybe you find something cooler than what I found. And obviously, you need to implement principle of least privilege. So specifically for machine learning environments, you can leverage the Atlas framework, which is like the MITRE ATT&CK framework for machine learning. As companies will tend to move towards leveraging such services, it's important that we don't mess this up. There is a page for threat matrix for storage services. So this is just for the storage offering from Microsoft. And you have a documentation of well-known techniques, procedures that adversaries use against these type of accounts, and these are certain resources to begin with. Atlas also enlists various case studies around simulations and incidents that are focused on ML environments that can help you understand and secure your own deployments. So finally, down to the acknowledgements. Really want to thank my family members, friends, my colleagues for helping me out in times of doubt. Zero Day Initiative for triaging and smooth communication of the bugs with Microsoft. There are a few more high-impact bugs in disclosure that we are excited about for next year, so stay tuned. And thank you, David and Magno, for all the help. It's not a question of if a vulnerability like this gets exploited someday, but it's a question of when. We need to secure our present first, and with that, thank you so much for attending this talk.